Yeah, I'll do it next time.
Sure.
Shall I try sharing my screen already?
Yes,
Yes,
please,
sure.
please try to share your screen and keep it. You are co-hostess, so you can do this now if you wish. Oh, great. Okay, great.
You're seeing
Who
it
is the
okay?
painter of this picture? John.
So I don't remember why I found this picture, but
I see.
sort of it, I found that it illustrated my physical intuition. So
Mhm. And what you prefer? What about the questions? Do you prefer to answer to the questions after the end of your talk, or you admit that people will interrupt you? What do you think, John?
I think it's fine if people ask me questions as we go along.
Okay, okay, good.
And of course, people could also put questions in the chat, but I don't think I can monitor the chat. But maybe somebody could monitor the chat and ask me if there's a question that I haven't noticed.
It is interesting if you ask ChatGPT to recognize who made this picture, can you get the answer or not? It should work.
Yeah, I don't know. Maybe if I go back and look at the original, I can figure out where it came from.
Okay.
I found it a couple of years ago, so maybe that's why I don't remember where it came from.
I'm going to close the door. Okay, now we can start in 1 or 2 minutes.
So, John, you'll be in Portsmouth next week, right?
Yes. That was why I was a bit confused when I got 2 invitations to give talks to or in Portsmouth.
Okay, yeah, later I got the email about your talk in Portsmouth. So, well, I will be happy to meet you in person in a week then.
Yeah, but that talk is going to have 0 overlap, I think.
Mhm.
Or maybe epsilon. It's a pleasure to see some old friends who are connected. I see Gianni Venturi, who may remember me from when I was a student. I see Chai Tian, and Philip, of course.
Yeah, hello.
Okay. People are still coming. Let's wait a few seconds.
I'm not in any rush.
Uh-huh. Who is it? Alexei Stravinsky is here. Okay. I think, hello everybody. I think we have a start. Now we have a pleasure to listen a lecture by John Ellis. He will tell us about astrophysical probes of Lorentz violation. John, 1 hour, please.
Okay. Well, thanks so much for this invitation, and very glad to have the opportunity to give this talk and meet up scientifically with some old friends. So we've already discussed a little bit this picture that's on my first slide. And this somehow illustrates the intuition that led us to the idea that Lorentz invariance might be violated, in particular, and perhaps somewhat surprisingly, by high energy particles. So here you see a bunch of ships in very rough water. And the intuition is that small ships, again, have more difficulty in going through this water than, let's say, a supertanker. So the small ships go up and down, and they're going to travel more slowly than they would do in calm water. And so the basic idea is that particles which have a short wavelength, or high frequency, high energy, might be more affected by fluctuations in the space-time background than particles which have longer wavelengths. So that's the basic idea. And after introducing this idea at a somewhat intuitive level, then I will discuss how this idea can be tested, is being tested using astrophysical sources. So the idea that Lorentz invariance is not sacred goes back quite a long way. And I'm sure that there are earlier references to this, but I found this paper by Dirac from 1951, which somehow gives a veneer of respectability to the idea that Lorentz symmetry might not be sacred. So I don't think there was a lot of activity in this area that I'm aware of, at least, until 1997, 1998, when almost simultaneously 3 papers talking about possible phenomenology of Lorentz invariance appeared. One by Coleman and Glashow, one that I was involved with, and one by Kolde and Kosteletsky. So I think we approached the idea from various different theoretical points of view. And in this talk, I'm going to concentrate on our particular point of view, which, as I said, was summarized on the first slide. So our approach was based on the idea of space-time foam. And so this is an idea which is conventionally ascribed to John Wheeler, in particular in this paper that he wrote in 1957, when he emphasized that if you looked at space-time on small distance scales, you could expect to see large local fluctuations, which would exist for short periods of time. And the picture on the right illustrates this idea. So down the bottom of these this stack of inverted pyramids, you have what space-time looks like on sufficiently large scales. You don't discern any quantum behavior. But as you look more and more closely, and if you can follow my cursor up the inverted pyramids, you eventually find that quantum effects would give rise to strong fluctuations on small distance and timescales. So that was the basic idea that we had proposed back in 1957. So here's the same picture again. And as I said, according to his ideas, one would expect quantum fluctuations in the fabric of space-time, which would be of order 1 in natural Planckian units. This, of course, was a long time before string theory, which introduced the possibility that there might be other scales associated with quantum gravity. So energy fluctuations of the order of the Planck scale, fluctuations on distance scales of order of the Planck length, lasting for something like the Planck time, and potentially also involving topological fluctuations of order unity. So this idea was, let's say, floating around, and back in 1996, 1997, we started thinking about what might be the possible manifestations of this space-time firm. And there was a bunch of different possibilities that we considered. One is the one that I'm going to be focusing on in this talk, namely that Lorentz invariance might be broken. But there are other possibilities that I might also mention. One, for example, is the possibility of a violation of the principle of equivalence. The intuition here being that maybe different types of particles propagating through this space-time foam would feel it or interact with it in different ways, and so their propagation might be different. Another possibility, which I'm not going to have time to mention, I think, in this talk, is that quantum mechanics might require some sort of modification or reinterpretation. And here the basic intuition goes back to Stephen Hawking in particular, who of course famously discussed the quantum properties of black holes and argued that they might exhibit transitions from pure states to mixed states, which would require some reformulation of quantum mechanics. So that's, of course, a very controversial idea, and I'm not going to go into it here. I should say that our ideas are equally controversial, if not more controversial. But anyway, we're going to fight on one front at the same once. Okay, so here again is the basic picture. Here we have small boats, which I would argue would travel slower than big ships in rough seas. Small boats correspond to particles with small wavelengths or higher frequencies, which maybe might travel at less than the conventional speed of light. The conventional speed of light, of course, being defined in the long wavelength limit. And this was something that we proposed together with Amelino Camelia, Nick Mavromatos, Dimitri Nanopoulos, and Sylvia Sarkar towards the end of 1997, and was published in Nature in 1998. So, just to emphasize our approach again, you have these intrinsic fluctuations at small distance scales, small time scales. As an energetic particle goes through, you would expect it to have gravitational effects. And these effects could interact with the intrinsic fluctuations, and you would expect some sort of back reaction on propagation of particles due to these interactions with the space-time fluctuations. And this would give rise to a non-trivial refractive index. Now, when we originally proposed the idea, we suggested, as I already mentioned, that the effect on particle propagation might increase with energy. And we had in mind that very possibly this would be linear with energy. So typically then parameterizes deviations from the velocity of light or time lags in the propagation of energetic particles linearly in energy with some energy or mass scale in the denominator, which we're going to be trying to probe with astrophysical sources. Now, it could be that the effect is there, but it's quadratic. And in particular, in the approach of Colliday and Kosteletsky, who proposed a Lorentz violation extension of the standard model, that's what they would expect. So what I'm going to be discussing later on, although I'll be looking more at possible linear modifications of particle velocities, I've also mentioned the possibility of quadratic deviations. Now, one of the reasons why we sort of started thinking about this was we were trying to formulate string models away from criticality. I'll say just a little bit about that in this talk, but this talk is mainly focused on the phenomenology. Anyway, in that non-critical strung model, we indeed found that the effect was negative, so that the velocities of energetic particles are less than the speed of light rather than more. And that's just as well, because if energetic particles propagated faster than the speed of light, of lower energy particles, then you get Cherenkov radiation, which is completely unacceptable experimentally. So originally, as I mentioned, we expected these effects might be related to a quantum gravity scale of order the Planck mass. But in non-critical string theory, you might get something different, because, of course, in string theory, you've got various different scales appearing at the string level. Okay, so this is the front page of our paper that appeared in Nature. And I circled in here the basic effect that we were thinking about in that paper, namely that to the extent that particles travel at less than the speed of light, you could expect a time lag in the arrival times of energetic quanta, even if they were emitted at the same time by the source. So, for example, consider gamma ray burster, for example. Gamma ray burster emits photons over a range in energies. It has a very well-defined time structure, but if the velocity of light decreases as the energy increases, then a more energetic particle would arrive with a time lag delta t, which would not only increase with energy, but also increase with the distance over which it propagates. So that's the basic effect that I'm going to be mainly talking about in this presentation. So just up here, top left, I've noted that at least as of yesterday, this paper got 1,310 citations. And I should mention that the other papers by Coleman Glashow and by Colliday and Kosteletsky have similar numbers of citations. So from a phenomenological point of view, probing Lorentz invariance, I think, is relatively popular. Okay, so this is a basic simple equation from our paper. So psi parameterizes whether it's positive or negative, the time lag, linear in energy, linear in distance. And what we suggested in our paper was to look at transient sources of energetic particles. In particular, at that time, we focused on photons. So you compare photons of different energies from some astrophysical source, which emits with over a very small time scale. And we pointed to a number of examples in our paper, gamma ray bursters, which were a big new thing in those days, pulsars, which of course had been around rather longer, and active galactic nuclei. So all of these have their advantages for probing Lorentz violation.
Can I ask a question here?
Yeah, please.
Yes, here it is assumed that all the gamma ray bursts are at the same time simultaneously emitted, isn't it so, in this formula?
No, so gamma ray bursters occur at different redshifts, i.e. different distances, and they emit at different energies. The point is that in any individual gamma ray burst, it tends to have a very well-defined time structure. A pulsar is another example where you get extremely regular emissions. Does that answer your question?
So the gamma ray bursts are from the same point and at the same time for this in this formula. This is assumed implicit.
Well, the gamma ray bursters occur all over the universe at different times. But if you look at the burst from one particular source, then it has this well-defined time structure.
But is it a good approximation to simultaneously assuming? Because, you know, in the burst and all the explosion, usually the slower ones come first out. For example, in sun 11 years cycle, when there is a burst, kind of burst, so the lights which are lower energies, they come first. They come from this, so they're from the surface, and then after that the burst starts, and then the very, very energetic comes after that. So maybe here there is one has to a little bit think to whether this is a good assumption that all the frequencies, all the energies have been at the same time simultaneously emitted. This is a remark.
Okay, so now I understand better. Yes, of course, this is quite possible. And if one wants to do a more complete analysis, one has to allow for the possibility that there is some sort of time lag at the source. And I'll say a little bit about how one can try to filter out that possible effect later on.
All right. Yes.
Okay. Excuse me, Philip. Excuse me, John. I see a question from Philip. Philip, do you want to ask a question just now?
Yes, sure. Yes, sure.
Please.
Okay. John, going back to work by DeWitt and Bream in the 1960s and stuff I looked at recently, it turns out that the Maxwell field, when it propagates in a non-conformal to flat geometry, the propagator takes support both on the light cone and inside the light cone. And so that's a fairly well-established concept. The only thing is, I don't know why you call it Lorentz violation. I mean, it's happening in a fully covariant theory.
Well, I call it Lorentz violation because it corresponds to a non-universality of the velocity of propagation. If you prefer a different name, make my day, but this is the way it's conventionally referred to.
I would just say it's propagation off the light cone.
Right. Well, that's not so catchy.
Okay, but it's also not as severe.
Right. Anyway,
Okay.
thanks for mentioning the work by Lewitt. Okay, so I just wanted to make one other remark about this slide here. So in our original paper, we sort of tabulated what we thought were the typical sensitivities. So what you see here is a compilation of distances, of typical emission energies, of typical durations of transients, and the corresponding sensitivity to a linear, if you excuse me, violation of Lorentz invariance. And that are all kind of comparable to within a few orders of magnitude. So pulsars, as I mentioned, emit extremely regularly. And there, I think there is really negligible time lag. But unfortunately, they're not very far away. And so they're not, they haven't turned out to be so useful subsequently. So most of the subsequent interest has converged on gamma ray bursters and on active galactic nuclei, with this as being a sort of prototype example. Well, I'll come back to that later on. So as I mentioned, it's sort of a corollary, or at least a possible corollary of this, that you might have a violation of the equivalence principle, in the sense that the amount of Lorentz violation might depend on the species of the particle, just because particles with different internal properties might interact differently with the space-time foam. So this is actually something which is of astrophysical interest, because there are extremely strong limits on Lorentz violation for the electron. And indeed, in our approach, it seemed to us that the violation of Lorentz symmetry would be more important for neutral particles, such as photons, neutrinos, and gravitons, than it would be for charged particles. And so later on, I'm going to be focusing more on probes of the constancy, or otherwise of the velocity of light for photons, neutrinos, and gravitons. Right, so this is just a little picture taken from one of our papers with Nick Mavromatos and Dimitri Nanopoulos, where we discuss a simple model for how relativistic particles in string theory might interact with defects in the space-time background, which are sort of modeled for the space-time foam. And we make the point that these interactions are non-universal, and so therefore you might expect that different types of particle would have their velocities modified in differing amounts, and in particular, charged particles in our model would not see this type of space-time foam, and they would propagate essentially normally, whereas photons, gravitons, and possibly neutrinos would be affected. So as I mentioned, there are actually extremely tight constraints on Lorentz violation for the electron. So this is a little bit off my main line, so I won't go into it in great detail. But this was pointed out by Jacobson, Liberati, and Mattingly, and they showed that if you had a linear violation of constancy of the velocity of light for electrons, then the coefficient of the linear coefficient would have to be bigger than 10 to the 26 GeV. However, this analysis doesn't give you any constraint on Lorentz violation for the photon. Okay, so photons. So let's consider emissions from gamma ray bursters. So if the velocity of propagation depends on the energy, if you have a source that emits a spike with photons of different energies, then any spike would tend to get smoothed out. And any structure in the emission would tend to be distorted, so that the peak would go down, it would get spread out at the wings, and to the extent that the effect has a definite sign, you would expect some skewness. So what we proposed, for example, in this paper here, was that you look at the data of photons from different energies, and you would look at their arrivals as a function of time, and you would try to restore irregularities as best you could. You would try to minimize the kurtosis, and you would try to minimize the skewness, because all those effects are things that are generated by Lorentz violation. And so this is a result from that analysis. So we used 8 different GRBs, and we tried to, if you like, restore the original emission structure of those GRBs as best we could. And we found that the sensitivity of this analysis was to a linear Lorentz violation of a few times 10 to the 17 GeV. So I'm going to go a little bit historically in the next few slides. So this was, for a while, the most stringent analysis for GRBs, gamma ray bursters. Then this is an analysis by the Hess collaboration of emissions from the active galactic nucleus. Oops. Sorry, I thought I turned off all my electronic communications, but apparently not. Okay, so they analyzed the temporal structure of gamma emissions at different energies from this active galactic nucleus. And they again tried to sort of restore the sharpest possible time structure of emissions. And what they found was a sensitivity to a linear violation of Lorentz invariance, which was very similar to what we had found previously for the gamma ray burster. So they looked at possible propagation within the light cone, but also outside the light cone. So the first of these, I think, would please Philip more. The second one maybe somewhat less, and it has these problems with radiating low frequency particles, which I mentioned. And they also analyzed a possible quadratic deviation from the universality of the velocity of light. We had also analyzed the possible quadratic violation, and again, their analysis and our analysis were kind of similar. Now, there's another effect which is very interesting, which was pointed out also back in the late 1990s by Kifune, and was developed by Prothero and Meyer in this paper that I mentioned here, which is if you've got a very energetic photon going through the background of photons, so there's a background coming from the cosmic microwave background, and there's also a background from just stellar light propagating between galaxies. then if you have a very energetic photon and it can interact with that background light and produce electron-positron pairs. This is a well-known effect. What they pointed out, Kafui, I guess, was the first, was that the threshold for electron-positron pair production, the energy threshold, would be affected if you have a violation of Lorentz kinematics, which is what would happen if you modify the relationship between a particle energy and its velocity, i.e. its momentum. And various analyses have shown that this effect on pair production of electron-positrons actually gives you a comparable sensitivity to possible Lorentz violation, in particular in the case of emissions from active galactic nuclei. So this is illustrating the point. Point is that normally you would expect, if you had essentially relativistic kinematics, that you would get electron-positron production, which would cut off the observed spectrum. So energetic photons emitted by the AGN would not reach us. But then if you do have Lorentz violation, depending on the scale of it, then this would modify the spectrum of photons at high energies. And we actually discussed this in connection with the Cherenkov telescope array, which is currently under construction, which would have fantastic sensitivity to this effect in the future. Anyway, what Hess found was that the spectrum of energetic photons coming from Markarian 501 was consistent with what you would expect from conventional kinematics of electron-positron production. They observed what looked like a cutoff, and they inferred a lower limit on the quantum gravity scale of a few times 10 to the 19 GeV. So as I mentioned, we also considered this possibility in connection with future observations by the Cherenkov telescope array of an AGN active galactic nucleus such as Markarian 501. And we found that the sensitivity would be potentially some factor times 10 to the 20 or 10 to the 21. So I think this is a very interesting topic for CTA in the future. And I know that the Cherenkov telescope array collaboration is thinking actively about looking for this with their future data. Okay, so collaborations looking for energetic photons, there's several of them, and they're very competitive. And I just showed you one from the Hess collaboration, a plot from the Hess collaboration. So here is an analysis from the rival MAGIC collaboration, where they analyzed a gamma ray burster, and they did a more or less conventional time lag analysis. And again, they got a limit on linear Lorentz violation of the order of 10 to the 19 GeV. So that's basically, I think, where the current sensitivity lies. The most recent paper looking at time lags is by Piran and Offenheim, which just appeared last month. And they looked at emissions from the brightest ever gamma ray burster, which emitted photons up to several TeV There's also some somewhat controversial emissions at even higher energies, and they again got limits on Lorentz violation, linear Lorentz violation, on the scale of a few times the Planck energy. So perhaps before moving on to neutrinos, I just wanted to make one point, which I haven't written explicitly on my slides, which is, of course, if you did start seeing an effect, you would not be convinced if you saw it in just one type of source, for precisely the sort of reason that Masoud mentioned earlier on. And you would want to look at many sources at different redshifts. You would want to look at sources of different types, so active galactic nuclei as well as gamma ray bursters. But that's a sort of moot point at the moment, because at the moment there's no positive indication for any sort of Lorentz violation. Okay, so now let me come to neutrinos. So neutral particles, so the sort of model that Nick Mavromatos and Dimitri Nanopoulos and I proposed, they might also exhibit slower than light propagation inside the light cone, as Philip would say. And so what can one infer about that from data? So this was discussed in the context of an accelerator experiment called MINOS, which is one of these experiments probing neutrino oscillations over distances of the order of several hundred kilometers. And they know precisely the time structure of their beam. They can measure the time structure of the arrival of the neutrinos in their detector. And so they were able to measure or set up a limits on the possible deviation on the velocity of neutrinos from that of light. And this gave them a constraint to linear Lorentz violation of the order of 10 to the 5 GeV, as was pointed out in this paper that I wrote with these neutrino physicists the following year. Subsequently, MINOS did a more precise analysis of the timing of the neutrinos, which corresponds to a somewhat more precise determination of the constraint on linear Lorentz violation for neutrinos. Now, you can also consider, of course, astrophysical sources, which I'm going to come to in a moment. As far as I'm aware, the first consideration of Lorentz violation from astrophysical neutrinos is also in this same paper, where we analyzed the arrival times of neutrinos from supernova 1987A in these three different experiments. So supernova 1987A is at a distance of about 50,000 parsecs, so 150,000 light years. These experiments observed neutrinos which were typical in the MeV range, but over a range of energies. And we were able to use that to set a lower limit on linear Lorentz violation for neutrinos of the order of a few 10 to the 10 GeV. So I see that there's a raised hand from Ariel. Ariel, you have a question or comment?
Maybe.
You're muted.
Maybe you can continue.
So I pressed a little button that says ask to unmute, but nothing happens. Ah.
No, I think everyone is muted actually. I don't see anyone open.
Okay, so I'm sorry, Ariel, that I can't hear you.
No, I'm just saying that I don't see anyone unmuted, so I think it's okay.
Okay, well, maybe Ariel can communicate his question in a different way. Okay, but there's been quite a bit of interest more recently in constraining Lorentz violation for neutrinos using active galactic nuclei. And this interest has been stimulated by the observations of highly energetic neutrinos, which seem to be coming from active galactic nuclei, which are also observed by gamma ray telescopes, in particular MAGIC and the Fermi satellite, as illustrated on this slide. And there was this paper that was written 5 years ago by a collaboration of the IceCube neutrino people and a whole bunch of gamma ray telescopes putting their data together. So here you see that the direction from which the IceCube neutrino came seems to coincide with the direction of this particular active galactic nucleus. So here you see that shortly after the neutrino, there was an indication of excess gamma ray emission in MAGIC. There was also an indication of extra gamma ray emission from the Fermi satellite. Other experiments didn't find such great indications, but maybe there's also some effect on some of these other experiments. So anyway, what you can do is you can compare the arrival times of the IceCube neutrino and, for example, this set of photons coming from MAGIC, and you can, to gauge the sensitivity, assume that they were emitted at around the same time. And just because the IceCube neutrino was extremely high energy of the order of 100 TeV, you get a very strong sensitivity to linear Lorentz violation for neutrino propagation. And that's what's shown here. And this is a corresponding constraint on quadratic Lorentz violation. And this was something that we wrote up in this paper, which was also published about 5 years ago. So here's a little bit more detail of the comparison between the arrival times of photons and the IceCube neutrino. And you can see that it looks like there's some sort of a coincidence between the photon emissions and the IceCube neutrino. So more recently, we've been analyzing data from IceCube, which are a cluster or flare of neutrinos coming from the same active galactic nucleus, but without any associated photons. So here the idea is that if neutrinos do indeed have an energy-dependent velocity, and if the source emits a cluster of neutrinos of different energies, then they will get spread out in time. And conversely, by looking at the arrival times of neutrinos, you can gauge the sensitivity to this possible Lorentz violation. And you can do this just by comparing neutrino arrival times and without requiring there also to be an accompanying photon flare. So this picture up here and this picture down here show you the time structure of the neutrino flare. And this shows that these neutrinos do indeed seem to be coming from the direction of the same active galactic nucleus that we were observing on the previous slides. So we can play the same game that we did earlier on with photon emission. So Lorentz violation would tend to smooth out structures, which you can test using Kolmogorov-Smirnov measures. The peak would go down, the tails would get wider, kurtosis, and there would also be an asymmetry induced in the signal skewness. So we simulated these possible effects, assuming various different amounts of Lorentz violation, and then we found what was the maximum amount of Lorentz violation, which seemed to be consistent with the data. And this is still a work in progress. We had hoped that we would have completed this analysis before I gave this talk, but we're still looking at the details, and we hear some preliminary results. We think actually the final results are likely to be a little bit more sensitive. So here we got a limit, or I should say a sensitivity to linear Lorentz violation of the order of a few times 10 to the 14 GeV. And for a quadratic Lorentz violation of a few 10 to the 8 GeV. And these vertical lines indicate the sensitivities or the constraints that we get from considering the Kolmogorov-Smirnov measure, skewness measure, the kurtosis measure. So stop press is that we discovered last month that there is another neutrino flare, which has been seen by IceCube, which is, in a sense, even more spectacular, because they apparently saw 3 energetic neutrinos within one day. So I've been trying to get details of this sort of mini flare from IceCube people, but it's proven to be quite difficult. But if these data are real, then they give you a sensitivity to neutrino Lorentz violation, which is linear Lorentz violation at the order of 10 to 16 GeV. So there are other IceCube energetic neutrinos which are associated with a different type of astrophysical event, which we hadn't thought about back in 1997, 1998. And these are so-called tidal disruption events, when a star is captured by a massive black hole. It gets disrupted as a process called spaghettification, where the star gets sort of squeezed out like toothpaste from a tube. And the plasma in the star is squeezed, it's heated, it emits X-rays, and apparently it emits energetic neutrinos. And by now, there have been several examples of tidal disruption events, which seem to be accompanied by neutrinos coming from the same direction. And here I've listed the ones that we've been able to identify so far. So we're mentioning these also in this paper that we have in preparation. Typically, they give you sensitivities to linear Lorentz violation of the order of a few tenths of 14 GeV. So here is a table of the constraints that we've been able to obtain. Well, I shouldn't say constraints, sensitivities that we found to linear Lorentz violation, which range up to something like 10 to the 17 GeV, or to quadratic to a few times 10 to the 11 GeV. And of course, these sensitivities are far beyond the sensitivities from accelerated neutrinos, or from supernova 1987A. But, they're getting to be, somewhat comparable to the constraints or the sensitivities that you get for photons. Any comments or questions about neutrinos before I spend a few minutes discussing Lorentz violation for gravitons?
Can I ask one question? It would be much easier to say that this Lorentz violation is the induced Lorentz violation, because you see the dispersion relation are depending on the interaction on the particle and so on. But while Lorentz symmetry is the symmetry group of the particle, and it is all its relation are universal. So everything happens in a medium. So by definition, it would be better to call it, this is an induced Lorentz violation, and there will be no possible discussion. Do you agree with this?
Yes, no, I think that you're perfectly right. And indeed, the intuition that we have is that energetic particles propagate through a non-trivial medium.
Yes.
It's in some sense an inescapable medium. So if photons go through a conventional plasma, or they go through glass, they interact with that medium. But that's I'm not sure what's the right word to describe it. But that's a sort of artificial violation of apparent Lorentz symmetry.
Or in other words, in usual physics terminology, induced. It is the same as if you put electrodynamics in an external magnetic field or electric field, everything can be violated. But this is not due to quantum to electrodynamics, but due to the external field. So this is induced. I mean, this is the usual terminology one should. Okay. So what about to call all this thing induced Lorentz violation? Because the Lorentz group
if you want to induce, that's fine with me.
So it's all right, yes, induced, yes. So no discussion will be yes, right.
Sorry, it is induced by quantum gravitational effects as opposed to any sort of electromagnetic or other conventional medium.
Thanks.
Yeah, thank you. Gravitons. So you've all heard about the gravitational chirp heard around the world, which is due to the fact that the frequency of gravitational waves emitted from a black hole merger frequency increases with time during the in-spiral. In other words, the gravitational waves have different frequencies, higher frequencies close to the final merger itself. Now, you can compare so this is a plot here for the first black hole merger that was observed, showing over a period of a fraction of a second how the frequency of the gravitational waves increased. And that observation is in complete agreement with conventional general relativity. But if you had Lorentz violation, then the velocities of gravitational waves with higher frequencies would be different from those gravitational waves with lower frequencies, and you get a modification of the calculated shape of this chirp. And when the first result came out from LIGO and Virgo, we immediately jumped on this and derived a constraint on the Lorentz violation, which is an extremely weak constraint, but as far as I know, it was the first constraint on the Lorentz violation in the case of gravitational waves or gravitons. Subsequently, there was this fantastic set of observations of a neutron star merger where LIGO and Virgo saw the gravitational wave chirping. So in this particular case, the chirp lasted for several seconds. And also, for the first time, there was observed an electromagnetic counterpart to a gravitational wave merger. And so here you see the light curve photons observed by the Fermi satellite, and this is another satellite integral which also observed a similar effect. And subsequently, photons of lower energies were observed by many, many astronomical observations. But you can compare the arrival time of the initial pulse of gravitational waves with the arrival time of the photons, which are similar to within a fraction of a second. Well, somewhat less than 2 seconds, I exaggerated. And the coincidence of the arrival times tells you that energetic light and low, comparatively, frequency gravitational waves have the same velocities to within 1 part in 10 to the 17. So that's very interesting. But can one do better in the future? So this is where I would just like to take a couple of minutes to advertise an experiment that I'm involved in called AEON, which involves a bunch of universities in the UK. And what we plan to do is to observe gravitational waves and look for ultralight cold dark matter using atom interferometers. And this is a phased sequence of experiments. We're just at the first stage with funding from the UK to do a small experiment at Oxford to demonstrate the principle. So the principle is very similar to that of a laser interferometer. Laser interferometer, you have a light source, you have a beam splitter. The 2 parts of the beam follow different trajectories, and then you bring them back together and you look at the phase shift, which is induced possibly by the passage of a gravitational wave. So you can do the same thing with atoms, but in this case, the beam splitter is provided by a laser beam, which separates the atoms into a cloud of ground state and excited states. You then apply a second laser pulse, which reverses the populations. So the excited ones become ground states, the ground states become excited ones, and then they come back together. And you then look at interference patterns. And this interference pattern can be sensitive to the passage of a gravitational wave. And I'm not going to discuss it in great detail, but we're very interested in the possible gravitational wave astronomy of such things. And in particular, we would be able to observe gravitational waves in a frequency range, which is different from that observed by LIGO and Virgo, and also different from that which is going to be observed by the LISA space-based laser interferometer. Anyway, the reason why I'm mentioning this is because you can observe those gravitational chirps that I was mentioning earlier on over a longer period of time and over a longer range of frequencies. And that gives you sensitivity to Lorentz violation, which is potentially orders of magnitude better than what's been achieved so far by LIGO. So this is something for the future, but it illustrates that looking for possible evidence of Lorentz violation is something which has interesting possibilities for gravitons as well as for photons and neutrinos. So that brings me to the end of my talk. This type of Lorentz violation is a speculative possibility suggested by our intuition about quantum gravity, space-time foam. The strongest phenomenological probes use astrophysical transients, gamma-ray bursters, active galactic nuclei, and so on. The constraints on Lorentz violation for photons are about 10 to the 19 GeV for the energy scale of linear Lorentz violation, about 10 to the 17 GeV for linear Lorentz violation. For neutrinos, the constraints on gravitons are much weaker. But we can expect much stronger probes in searches for future transient astrophysical sources. So all this is very nice. It's attracted a lot of phenomenological and experimental interest, but it would be nice to have a better formal basis for these speculations. Thank you.
Okay, thank you very much, John, for your very interesting talk. Questions, please. I see one question, but I don't see from whom. Ah, okay. Richard, please ask your question. Can you hear me?
I think you have to mute. You are muted, Richard.
Please.
Sorry. Lorentz violation automatically means Poincare violation, but not vice versa. There were papers, they called it kappa Poincare. It was the formation of Poincare algebra. And by the way, it was Amelino Camelia and Lukierski. What is your opinion of that?
Yeah, well, I must admit, I haven't followed in detail those theoretical ideas. I think Amelino Camelia got sort of inspired by this joint work that we did to think about what might be a more fundamental theoretical framework to describe it. But I'm afraid I haven't looked at it in detail. I should add that Amelino Camelia has also had some speculations about Lorentz violation for Ice Cube, which again, I haven't been able to follow in detail.
Yeah, they claim that redshift can be somehow explained by this Poincare, kappa Poincare deformation.
Yeah, well, okay. I'm guilty of a lot of speculation, but I think that speculation is even beyond my horizon.
Thank you.
Okay, the next question is from Sravan. Sravan, please ask your question.
Hi, John. Thanks for the very nice talk. I have a couple of questions. The first thing is about, well, when you mentioned this Lorentz violation tests from different sources, I'm wondering what would be, do you consider the effect of curved spacetimes? For example, I mean, you are looking at different sources, right? So I'm assuming the gravity will have an effect on the particles, so especially dynamical nature of gravity. So can you comment something about this?
Yeah, so all these analyses, so we're looking at sources at cosmological distances. And so what we assume is the standard lambda CDM. No, of course, as we know, there's various tensions with that model, but I think that the tensions are at a level that don't really, are not really important enough to affect our analysis. But basically, the only effect of the background that we consider is this quantum effect at Planckian scales. We don't consider other effects. But I don't think that modifying the cosmological model would be significant.
Okay. And my second question is about CPT. Is it, when you say Lorentz violation, is it also mean CPT violation?
Indeed. I didn't emphasize that, but when we speculate about quantum mechanics violation, yes, we violate CPT. But that's a whole different kind of worms. And we have looked at phenomenological constraints on CPT violation, which you get in particular from meson mixing and oscillations. And back in the 90s, we looked at that in connection with kaon mixing and oscillations. And more recently, there have been constraints from mixing and oscillations of other types of mesons, in particular B mesons. But the sensitivity, I think, is not any better than what we got from considerable K mesons.
Okay. Thank you.
Okay.
Again, sorry, let me just add. So the sensitivity that we got was again of the order of the Planck scale. There seems to be some sort of phenomenological wall that whenever you do these probes, then you find that you can sort of effectively rule out effects which are at much longer scales than the Planck length. But once you get to the Planck length, you don't seem to be able to do any better.
Okay, and maybe just while you are explaining this, I was thinking, what about early universe physics? Because most of the things you spoke about are astrophysical sources. But if the Lorentz violation is much more relevant in the Planck scales, surely signatures of inflation should show in some way the Lorentz violation.
Yeah, well, yeah, I think that's a good thought. The obvious place to look is the cosmic microwave background radiation, because that was emitted. No, that's the earliest stuff that we can look at. Unfortunately, the cosmic microwave background radiation has a very low energy, although fluctuations in the CMB, of course, are due to effects at a very high energy scale, presumably during inflation. But that's not directly visible in the CMB that we see. So I thought a little bit about that, but I haven't come up with any good way of testing Lorentz violation there. But that's maybe something worth thinking about in more detail.
Maybe non-Gaussianities or cosmological collider physics would shed some light on this, rather than, of course, two-point correlations are, maybe it's difficult to see any signatures.
Right.
Okay. More questions, please. I don't see that people supposed to ask. Okay. Or maybe I will ask some general question. Suppose, John, you have unlimited amount of money. What experiment can you propose to start?
You mean an experiment to?
No, the experiment which related with a probe of Lorentz violation. So suppose you have infinite amount of different resources, something like that. What do you prefer like to do? Okay.
Well, I think that I would. Am I allowed to split my resources? If I'm allowed to split my resources, I would make Ice Cube 1,000 times bigger. And I would make CTA, the Cherenkov telescope array, 1,000 times bigger. Well, 1,000 times bigger wouldn't fit on the Earth, but you know what I mean.
I see. Oh, thank you. More questions? If not, let's thank John once again for very interesting talk. And please don't forget to send us your presentation, okay?
Okay, my pleasure.
And me, John.
To Alexei, I don't know, maybe. Okay.
Thank you very much.
Okay, bye, folks.
Bye-bye. Thank you.
Thank you.
Thank you.
Thank you. Thank you very much.
Thank you very much.
Okay, my pleasure.
Thank you. Bye-bye to all.